Test 1, we selected several road sections within and around UiTM Shah Alam campus. The selected location represent different traffic loads, pavement surface conditions such as near faculty building, main access road and parking areas. These areas were chosen because they experience frequent vehicle movement and are exposed to weather conditions that may affect skid resistance and water drainage. During site observation, we identify issues such as polished pavement surface, water ponding after rainfall, and uneven texture, which could potentially compromise road safety.
Our group conducted a detailed field data collection to evaluate skid resistance, surface texture depth, and surface drainage efficiency at the selected road section within UiTM Shah Alam campus. The purpose of this data collection is to obtain actual pavement condition data that can be used to assess road safety performance, particularly under wet weather conditions. Firstly, skid resistance was measured using a British pendulum tester, which is a standard apparatus commonly used to assess the frictional properties between the tyre and pavement surface. Before conducting the test, the pavement surface was clean and wet to simulate wet road conditions. This is important because skid-related accidents usually occur during rainfall. The British pendulum tester was then carefully placed on the test locations, ensuring it was properly leveled. The pendulum arm was raised to a fixed height and released, allowing the rubber slider to contact the pavement surface. The skid resistance value, also known as the British pendulum number (BPN), was recorded directly from the scale. To improve accuracy and reliability, multiple readings were taken at the same locations, and the average value was used for further analysis. Turning to the skid resistor results, we evaluate the surface friction using the British pendulum tester. Our measurement revealed that the rough surface provided the highest safety margin with an average BPN of 65.6 due to its superior microtexture. The medium surface followed with a BPN of 61.3, while the smooth surface recorded the lowest resistance at 53.3. While all surfaces technically meet the standard safety threshold for good skid resistance, the lower for the smooth surface highlights a higher risk of hydroplaning. This confirms that as surface roughness increases, the mechanical interlock between the tyre and the pavement improve, which is vital for effective braking in wet conditions.
Next, the surface texture depth was measured using the sand patch method, which is a simple yet effective technique for determining the microtexture of pavement surface. A known volume of dry sand was carefully poured onto the pavement surface. The sand was then spread evenly in a circular motion using a flat disc until it filled the surface void and formed a uniform circle. The diameter of the sand circle was measured in two perpendicular directions, and the average diameter was calculated. Using this measurement, the mean texture depth (MTD) was calculated. This value represents the roughness of the pavement surface, which directly influences both skid resistance and water drainage capability. Pavement with a higher texture depth generally provide better friction and allow faster removal of surface water, reducing the risk of hydroplaning. Based on the sand patch method result, the surface texture depth varies clearly between smooth, rough and wet pavement surface. The smooth surface recorded the largest average diameter and the lowest texture depth of 0.022 cm, indicating a polished surface with minimal microtexture. This condition limit water drainage and may increase the risk of skidding. The rough surface show a higher texture depth of 0.099 cm, reflecting better surface roughness and improved tyre pavement contact. The wet surface recorded the highest texture depth of 0.156 cm, as shown in the bar chart. This indicates deeper surface void that allow more effective water drainage and reduce hydroplaning risk. Overall, the results show the higher texture depth improved drainage performance and road safety, particularly under wet conditions.
Pavement permeability measurement. In addition to visual inspection, pavement permeability was evaluated using a falling head permeameter, also known as a pavement permeability tester. This test is used to assess the ability of water to infiltrate through the pavement surface, which is a key factor in surface drainage efficiency. The permeameter was placed firmly on the pavement surface to form a watertight seal. Water was then filled to known height inside the device. As the water infiltrated into the pavement, the drop in water level over time was observed and recorded. The permeability coefficient was calculated based on the change in head and the elapsed time. Pavement section with higher permeability value allow faster water infiltration, reducing surface water accumulation and hydroplaning risk. These tests provide a quantitative assessment of drainage performance, completing the skid resistance and texture depth measurement. Looking at our result from the falling head permeability test, we observe a clear variation in flow rate across the different pavement surface. The medium surface exhibits the highest flow rate at 63.51 m3 per second, suggesting a higher interconnected void ratio. Interestingly, the rough surface followed at 52.39 m3 per second, while the smooth surface recorded the lowest drainage capacity at 55.37 m3 per second. These data indicate that surface texture significantly influences permeability, with medium coarse texture providing the most efficient drainage path, which is critical for reducing hydroplaning risk on a road surface.
All test results were compared with relevant design and performance standards to determine compliance with acceptable safety limits. The comparative analysis demonstrates that pavement section meeting the recommended skid resistance, texture depth and permeability criteria provide better safety performance. Sections that fail to meet one or more of these criteria were identified as high-risk areas requiring improvement through maintenance or surface treatment.
Based on our analysis, several improvements are recommended, such as surface retexturing, proper maintenance scheduling, and enhanced drainage design, particularly in high traffic areas. Regular monitoring of skid resistance and texture depth should be incorporated into pavement maintenance practices. In conclusion, this project demonstrates that effective integration of skid resistance, surface texture, and drainage efficiency is essential for safer and more sustainable road infrastructure. This study supports Sustainable Development Goals 9 and 11, promoting resilient infrastructure and sustainable urban mobility.